All right. Simple harmonic motion. Not so simple, is it? All right, all right. So this one's acceleration, right? So remember, in a simple harmonic oscillator, right, we've got x is 0. Here it is at some, it oscillates back and forth. So here it is at positive x naught, right? And here it is at negative x naught, right? And so this object is, got a spring, we've got a mass. They don't really talk about this, but there really is a mass, there really is a spring constant here. This thing maybe is, has already gone to this position. It's on its way back here, right? Okay. Remember that in the middle, there's no potential energy, right? So there's no, PE is 0. Okay. And at the edges, of course, that's where it stops and turns around and goes back. The kinetic energy is 0, right? So at the edges, right? And in between, like right here, the total energy is going to be the kinetic energy plus the potential energy, okay? So this thing's going to oscillate back and forth. And we've got some really good formulas here, okay? So just take a look at this guy. This one is the relationship between period and frequency, right? So literally period is the seconds per cycle, right? And frequency is cycles per second. So these guys are inverses of each other, right? And then this one relates the angular velocity of this, right? Of this harmonic oscillator to the period, right? So omega is going to be 2 pi divided by that period, right? Okay, so if they give you the period, you can find the angular velocity, right? And then this is the acceleration of this thing, right? Okay, and this is kind of fun, right? Because we can figure out the omega from this, right? We can plug the omega in there, and then we've got this thing, and then there's this funny minus sign on there. Well, remember the Hooke's force, right? Is minus kx, right? Okay. Well, F equals, that also equals ma, right? Okay, so that means that the acceleration of something is minus k over m times x, right? A is also equal to omega squared minus omega squared x, right? That's this formula right here. Okay, so that means that omega is the square root of k over m. Isn't that fun? And you can, of course, you can get that from this too, right? If you divide 2 pi by the period, right? And then the 2 pi over this, right? You get that omega is square root of k over m, right? They've got that there, but this is a good thing to remember, right? Okay, so this is this, right? Period is, and this makes sense, right? The more mass you have, right, and the longer the period is, the stiffer the spring is, right? That's the spring constant, right? That's going to be newtons per meter. The amount of newtons you need to stretch at a meter, right? Okay. The stiffer the spring is, the shorter the period is, right? This is for a simple pendulum. So this is the length of the pendulum. This is 9.8, right? Unless you're on a different planet, and then it's like, whoa, look out. Okay. Yeah, okay, so we've got that. And then here is, this is fun, right? So this is, if it's sine, right? Notice that this is velocity, right? That's just dx dt, right? So you calculus people realize that cosine is the derivative of sine. And so if this offset angle is 0, right? Then we get a nice, it's going to be a sine wave, right? Okay. The velocity of this thing, right, is going to be like this, right? So you can see the slope on this guy, where the slope on this guy is 0, the velocity, the cosine is 0. Oh, no, don't want to do that. Okay, so that makes sense, right? Where this thing is the maximum steepness, right? Then the velocity is a maximum negative thing. Here, the velocity is some maximum positive thing. So this all works out, right? This is time tested and true. Notice that x naught, that's the amplitude, right? Here, the amplitude of this guy is omega x naught, and that's because tangential velocity is just omega r, right? And there's an analogy between a rotating object and an object that's undergoing this simple harmonic motion. If we only look at the x coordinate of a rotating object, and that's why this all works, right? Okay, and then they just put this offset angle in there so that we could start instead of here, we could start here, or we could start here, or something like that, right? Actually, you don't even need sine and cosine. You can just do sine and just add an offset, right? Okay. This guy is the speed of something. Really, that's speed because it's plus or minus, right? Okay. The speed of something is, let's say this thing is here. We say that the object is right there. That's its position. That's not at the amplitude, right? Okay. And then this is the maximum position there, right? So we're saying that the speed of something is literally, and this is just Pythagorean theorem here, by the way. The speed of it is just plus or just omega times the square root of the amplitude squared, right? Minus where it is now squared, right? So if you are in the very center, this thing under the radical becomes a maximum because x is 0, right? Okay. And when you're out at the edge, x is equal to x naught, and so this is 0. The velocity is 0. The speed is 0. Okay. And then the total energy is given by this. This is our total energy, right? I hope you recognize that that's just this. They just stuck that. That's the maximum velocity, right? That's v naught. That's the maximum speed. They're just saying that it's 1/2 m times the maximum velocity squared. That's just kinetic energy, 1/2 mv squared, right? So that happens, by the way, at the very center, right? In the center here, we're moving at whatever that maximum speed is, right? Okay, and at that point, it has no potential energy, so all of its energy is kinetic, right? Therefore, the total energy is whatever the kinetic energy is at the center, right? And then this one is the potential energy, right? So at any given point, the potential energy is given by this, right? And you're like, well, how does that work? Well, we got to figure this out, right? So 1/2 m, omega is just square root of k over m, right? We figured that out here, right? Okay, and we're going to square that, right? I'm just plugging into this squared times x squared. Well, by gum, if we do this, we get 1/2. Let's see. If we square this thing that is square rooted, the radical just goes away and the square goes away, right? So k over m times m is just k. I hope you see that this is just the Hooke's law potential energy equation, right? Where it's the potential energy is 1/2 kx squared. So that's literally what this guy is, right? Now, what if they ask you for the kinetic energy at a certain point? So you can calculate the potential energy. They say it's got this amplitude and it's got this period and it's got this mass or something like that, right? And then they say, well, what's its potential? What's its kinetic energy at a certain position? Well, we can just do this, right? The total energy is the potential energy plus the kinetic energy. So plug the numbers into the total energy equation right here. Let's say maybe it's 60 joules or something like that, right? And then plug the numbers into the potential energy one. Maybe it's got 40 joules of potential energy, right? Well, then our kinetic energy has to be 20 joules, right? You can just use conservation of energy to calculate that, right? I just pull these numbers out of the hat. They don't come from anywhere except for my twisted mind. Right? I don't think there's anything else to say about this. I better stop talking.